Hello, my name is Axel Roest and I'm going to talk about full stack Swift with Arduino. Now, what do I mean with full stack? For most people, full stack means the web, APIs, databases, web servers, websites. And yes, also, but for me, this talk, full stack means the Internet of Things. So connecting from an edge device to the cloud. Case in point, we're going to make our own IoT appliance. I have some plants, but I'm very bad at maintaining them and I often forget to give them water. So I thought, well, it would be nice to have a little sensor in the plant pot, which informs me that the plant needs water. And so what I did is I have the plant pot, I put a little moisture sensor device in it and connected to a small embedded controller called an Arduino, which you have one right here. And the Arduino is very nice. It has many input and output ports, so you can easily connect it to the other devices. The Arduino collects the data and then sends the data over the serial port to another computer, which is a Raspberry Pi. Let's go there, which is this one. It is much more powerful than the other one. This one runs Linux and can connect to Wi-Fi and Ethernet. And so this one can distribute the data from the Arduino to the web and provide an API for the mobile phone application. So this is a whole setup for a sensor device to your mobile phone. Now normally the Arduino is programmed in a language called C++. And then it sends the data out over the serial port to the Raspberry Pi, and on the Pi you probably need something like Python to inject the data into a database. And then the data can be distributed by anything which can create a website like Node.js or PHP or whatever you want. And then of course you can create a mobile phone app using Objective-C, but luckily nowadays we can do that in Swift. We'll get back to this picture later. So to recap, we need to create an Arduino app. We need to create some sort of application that takes the serial port input and puts it into a database. We need to create a backend, an API and a website. And we need to create a mobile phone app. So we have lots to do. Let's go. But first, what is an Arduino? An Arduino is a small device. It's an open source electronics platform created in Italy in 2005. And it is a robust controller. It doesn't have any OS running on it. So you program bare metal. It's hugely popular with the tech crowd, but also the non-tech crowd, and artists have embraced it to create all kinds of weird things and installations. So here, for example, are some projects done with an Arduino. We see home automation on the left. We see someone who created a walking cat. Robot devices. People have made hand gesture input devices. Step counters using accelerometers in shoes. And someone even created a robotic hand. And also many people create instruments with it, and it's, as I said, it's very popular. But the problem is, you program these Arduino in a language called wiring. And wiring is in a turn based on processing. And in the end, wiring is implemented in C++. So basically, it is C++. So what does it look like again? It looks like this. You have on the top, you have your hash defines, which define constants. Then you have a hash ifdef to determine which library you have to take. And you see integer declarations, and you see a function call with unnamed parameters. And on the bottom, you also see a C-style for loop. So every time I switch back from iOS or Mac development to embedded development, I get all these mind swaps. So, for example, I created a little device recently which needed to be used in multiple locations. So I needed an array with multiple Wi-Fi networks. So I create an array, but arrays in C string arrays in C are terrible. So I thought, okay, let's create a C++ string array. But then the Wi-Fi library needed C strings, so char star arrays. So I had to convert from C strings to C strings, and every time and then you deal with void star pointers, and it's like, every time it was a mind swap, and do I need a string copy or a string copy? So luckily, Swift to the rescue. A couple of years ago, Dylan McKay created an LLVM-based cross-compiler for the Atmel processor. So what does it mean? It means you can create Swift code, run it through the LLVM, the low-level virtual machine, and create code for this little device. So before I continue, let's talk a little bit about terminology, because I'm talking about Arduinos. So what is an Arduino? Arduino is the board and the platform that is created, which you can use as a hardware developer. And then the Atmega is the processor which is on that board. And there are multiple variants of it, very small and very big ones with multiple connectors. And then the Atmega is part of the AVR family, which is in turn created by the Atmel Corporation. So a year ago, a friend of mine, Carl Pito, used that LLVM cross-compiler and created an IDE called Swift for Arduino. So what is Swift for Arduino? It is a standalone IDE. It incorporates the LLVM and cross-compiler, the Swift compiler for the Atmega. It has a built-in uploader, so you can directly create the binary that you compiled to your Arduino device. It is independent of the Arduino application, and it is also independent of Apple. So the nice thing now is that libraries can also be in Swift, and you don't have to write them in C++ anymore. So let's show a little bit what this integrated development environment looks like. On the right-hand side, you see your source panel. It's the same as in Xcode. You have your Swift source code here, and you have tabs to show different source files. On the left, you see your snippets panel. And the snippets are small pieces of code or statements which you can use in your program, which are not standard Swift, but especially created for the hardware environment. So we see things like connecting to software, to analog and digital pins, or reading sensor devices, or talking to hardware buses like I2C and SPI, and also connecting to NeoPixels, which are nicely RGB colored pixels, which you can use. On the top, you see your build button and your upload button, like the run button in Xcode. And you also have a little drop down where you can select which Arduino you want to upload to, because you can have multiple Arduinos connected to your Mac. And then on the right hand side, you see toggle switches for other panels. So for example, on the right here, you see your console, which shows the build status, any errors that might occur, and the upload status when you're uploading to your device. And on the bottom, you see a serial console to talk directly with your Arduino. Now, what would the hardware talk be without a blinking demo? So here you see some examples what you can do with NeoPixels. So these are small RGB LEDs which you can drive directly from your Arduino. And people use them a lot to make Halloween displays and for all kinds of fun projects. So there is a problem with Swift for Arduino, and that basically has to do with the fact that it is a very small processor. The processor is 8-bit and only contains 2 kilobytes of memory. And that's like 1,000,000 times less powerful than your standard iPhone. So the Swift runtime is a lot smaller than the Swift runtime that you would run on iOS or macOS. So even though it does support Swift 5.3, several Swift features are missing. What is missing? Classes, dictionaries, and dynamic strings. And these have mostly to do with memory constraints. Remember, your iPhone has a huge amount of memory compared to 2 kilobytes. And especially classes and dictionaries are dependent on also the runtime, which does things in a multi-threaded environment. And this processor does not support multi-threading, at least not in the way that we're used to. Also, dynamic strings, especially UTF-8, takes up a huge amount of RAM, and we don't have that. Another important thing is predictability. When something takes like a millisecond on your iPhone, you get a millisecond delay, you don't really notice it. But on an embedded device, which controls motors and lights, that 1 millisecond might mean that the robot arm is suddenly not here, but there, and you might hurt someone. So predictability, that things happen exactly when you want them to happen, is very important in embedded devices. So you don't want multi-threaded things in the background, which takes up a huge amount of time. So Swift for Arduino currently does not support multi-threading and to prevent unpredictability. Partly implemented are arrays and strings. Now, arrays on iOS and macOS are great. They're sort of magical things. They're very quick, but when you change anything, a background operation starts, which copies the whole array and does copy on write, which also means unpredictability, because you don't know when that is going to happen. So when your array grows from like 100 items to 101 items, suddenly that operation is a lot slower than you expect, which is unpredictable, which you don't want. So arrays are best allocated at the start of the program and a fixed size. And also strings, string interpolation is not supported, and dynamic strings are also not supported. Because strings are hard-coded in the program. These little Atmega processors don't have the von Neumann architecture that most processors, real big processors, have. They use something called the Harvard architecture, where program space is completely separate, is a completely separate address space than your application data. So your program does not run from RAM. Your program runs from ROM or flash. This also means that a lot of things that have to do with dynamic strings are hard to implement, because then we have to copy the strings to RAM to be able to do things with it. To work around this, there's a separate string class called AVR string buffer, which does limited things so that you can use strings in your application. On top of that, there are additional functions that you need for hardware and embedded devices, which you don't have on your phone. For example, you can read and write analog values. You can read and write hardware digital pins. You can steer NeoPixels, and you can have sensor libraries to measure humidity and temperature and the moisture of your plants. And of course, it supports hardware serial protocols like I2C, which is an inter-chip bus, and SPI, and of course a serial port. And yay, we now have closures in embedded development, which is great. But also that comes with a caveat, because closures inside structs which encapsulate self need a lot of runtime support. And again, we don't have much runtime support. So closures can exist, but you cannot access only global variables, which is okay. If you want to learn more about this, there's a special YouTube talk from the implementer of Swift for Arduino. So up till now, I talked about Swift for Arduino version 4.1. Let's have a little sneak peek what the next version will bring. The next version is 5.0, and we'll try to have better command line tools. So we will have command line tools for compiling, for uploading, and the application. And we try to have better C++ integration, and our goal is that you can use a standard Arduino C++ library, drag and drop it, and then it will create a Swift encapsulation of that library. So it's really easy to use the huge amount of libraries that are out there for the original Arduino. So back to the project. So we already have a phone that we can write in Swift, a mobile phone app. We can, of course, with server-side Swift, we can create a website and an API. And with command line Swift tools, we can create an application that takes the serial port and inject it into a database. And now, with Swift for Arduino, we can also create an embedded device fully in Swift. So everything can be done in Swift. Let's make this. But first, protocols. Protocols, and I don't mean the Swift protocols, I mean communication protocols. Because between a website or an API and your mobile phone is clearly defined what you can use. There's HTTP, you have JSON, XML if you even. But between the Arduino and the Raspberry Pi, it's not known. You have to define it yourself. So what can you do? You can use JSON, but JSON is not a stream format. Basically, it's only a simple value that we send over the serial port. So we can just send the values. But then you might run into problems that one value overlaps the other value. So it's nicer to put little tags around it so that you know, okay, when the opening tag comes, this is the value, and the closing tag, this is the value. So you have a packet start and end, basically. So we have 4 steps to do. Let's start with the Arduino program. Remember, there is no OS. There is no OS demanded run loop. We have to do everything ourselves. So normally an Arduino application consists of a setup part where you define your in and output ports, and your main run loop where you measure values and you set pins and you upload or you send values to another device like we do here. So what does it look like? In the top we import AVR. This is the AVR, the library for the Atmega processor. And we define some pins. So we said, oh, the LED is on pin 7, and we have a debug pin which we use, and with the sensor is on pin 0. And we define some constants where we want to blink LEDs. And then we set a low and a high set point, so when there is enough water and when the plant needs some watering. Then in the setup, we define the serial port speed and we define the pin modes. So we define here 2 pin modes, output pin modes, and the analog pin is always an input pin. And we also set up the NeoPixels with the fast setup iLED library. So to be able to blink RGB LEDs. And at the bottom, you see a thing called setup watchdog blinky. Now, with hardware, it's always nice to know if the device is still running. And what I do there is to make a little blinking LED so that you know, oh, the device is still running correctly. If you just have a LED on the power, it's like green, but you don't know if your program is still running or if it's just the power is there and your program crashed. So it's nice to have a little blinking LED. And I do that using an interrupt callback routine, which I set up here. So every 2 seconds currently, this routine is called, and I set a global variable blinking to true, and I set up a hardware pin, and that's always handy to be able to debug your application using oscilloscope. So then in the main loop, we measure the moisture and send the value over the serial port. You see in send value that I have the square brackets around the value that I'm sending. Now you also see analog read sync. Now you have to know that reading an analog value can take up 100 microseconds on your embedded device. So 100 microseconds, you can do a lot of things if you want to. You can set servos or something. But in this case, I don't care about that. I cannot do anything without this analog value. So I just wait synchronously until the value is measured, and then I send it over the serial port. And if I want to do something else, I have an analog read async, of course, with a callback routine. Then, after the setup is done, the main run loop is very easy. I determine if the blinking is set by the interrupt callback routine, and then I do a measurement and I light up the LED. And when the alarm is triggered by the moisture measurement, I'll do a different routine and I'll show the alarm, which is a red LED. So what does it look like? Here you have, on the right, you see Swift for Arduino IDE, and on the left you see my little demo setup. When I start the upload process, you see the program is being compiled and is being uploaded to the Arduino, and as soon as it's uploaded, the application starts and you see a blinking green LED to show that the application is running. Now I can simulate the moisture of the earth by turning a potentiometer, which is a variable resistor, so to simulate the measurement of the earth. And when it's too dry, the LED starts turning red and blinking. At the same time, I can also show the serial console, and you see when you start the application that the values are sent over the serial port. This is also great for debugging, of course. It's like the console in Xcode. So this concludes Swift for Arduino. What next? Data injection. So we collect the data that is sent out by the Arduino over time and need to inject it into a database. So serial port, SQLite database. So normally I would do this using a shell script. For example, you have your serial port and the output of that you put through a stream editor where you massage the data and then you insert it into SQLite. This is the Unixy way, small tools for small things. So I started with that. And on the top you see an STTY program which sets the baud rate. And then you cat the device, the modem device, and you pipe it through SED, stream editor. You do some things with it, and in the end you pipe it through SQLite, and it is inserted into the database. But this is arcane knowledge. For example, you have to keep STTY running with the ampersand on at the back, because otherwise the serial port defaults to its normal value and you lose the baud rate. So you have to keep that running. Also, the set command, it's regular expression, but all these things with the date time and current timestamp, so this is terrible. So there should be a Swifty way. And there is, of course. So I start a little Swift program and I create an SQLite handler and I create a serial handler. So the serial handler gets the serial port and then uses an SQLite injector to call the routine which inserts the information the packet received into the database. And the serial handler uses a nice package that I found called ORS serial port. And ORS serial port has a feature where it can scan for packets in your data stream, in your serial stream. So here you see a prefix string and a suffix string. And what it does, when it encounters those strings, it calls the delegate method did receive packet, and it gives you the string that it found, which you can then directly insert in your data injector. And then the data injector calls the SQLite write routine to insert it into your database. So what is the database schema? I'm going to talk about that when we talk about Vapor, which is now. For the backend website, I wanted to use server-side Swift. And there are many server-side Swift solutions. You have Perfect, you have Kitura, but I was already familiar with Vapor, so I'm going to use Vapor. We're going to create a standard Vapor app. So a standard Vapor app has a router which connects the endpoints, the REST endpoints, to functions in your application. And we need a website and we need an API for the data for the mobile phone app. And it all connects to the SQLite backend because we already have an SQLite database, so we can use the same database. Our data model is very easy. We have sensors and we have readings. And a sensor only has a name and an image, and the readings connect to the sensor and have a date and a value. Nothing fancy. And when you run your Vapor application, there's a website and it shows the sensors, which are the plants, and the values of those readings. And in this case, the aloe vera didn't have any reading yet. Also, I'm not a front-end person, so this is basic functionality. We also have an API. So this is the API for the sensors, where you see, the sensors. And there's readings which are connected to the sensor ID. So we can use this API for the mobile phone app. But this is not a Vapor talk. I'm not going to explain how this Vapor application works. There are plenty of Vapor talks. Please look there. My code is, you see on the bottom right, is on my GitLab page. So I developed all this on my Mac because I'm already sitting behind the Mac. It's nice and easy and comfy, but there's a danger, there's an inherent danger of Mac development when you're actually developing for Linux. For example, this nice library that I found over a serial port, which has a Swifty interface to the serial port, only works on Darwin, so macOS, because it uses the IO Toolkit. So it doesn't know anything about Linux. It uses the IO Toolkit library frameworks to connect to hardware. So I found another library, which is called Swift Serial, to connect to the serial port, but that had issues with multi-threading and baud rate problems. So you set it to a certain baud rate and then it would default to another one. Also, there were SQLite problems. I found a library called SQLite Swift, which I thought, nice and Swifty. But it worked fine on the Mac. But when I switched over to Linux, I got these weird error messages that I were almost unable to Google. So when I was making this presentation, I thought, oh dear, maybe I should go back and deploy my application on a Mac Mini server. But luckily, perseverance, and after testing out 4 other SQLite libraries, I finally found the perfectly Swift SQLite library, and I was able to run my application on the Raspberry Pi. Yay! Hooray! So the next part is the mobile application. And for the mobile application, I'm going to create a Swift UI application. What does the application need to do? It's very simple again. It needs to connect to the API and it needs to display the results in a list. So what does it look like? We have our plant list, and when everything is hunky-dory, everything is green. But when a plant needs watering, the display changes. You get a warning message on the top and it shows the plant which is in dire need of water. We're not going to go into the Swift UI because this is not a Swift UI talk. Plenty of Swift UI talks, and please look over there. But also the code for the Swift UI app is on my GitLab page. Conclusions. We can now create a fully Swifty IoT chain from the sensor, the edge device, to the cloud and your mobile phone app. We can do data injection, we can have an API, we can have a website and a mobile frontend, all in Swift. Other conclusions. Swift on Linux is still hard, has caveats, and also hardware has the word hard in it for a reason, because so many things are undefined and not very common when you do Swift development. Still, I believe Swift for Arduino is a step in the right direction because it allows for safer embedded development. You have strict type checking, you don't need to deal with pointers and memory leaks. And currently Swift for Arduino supports the Arduino Uno incompatibles, which is the Atmega 328P chip. And hopefully this year we also support the Arduino Mega. And Maybe next year we'll support Espressif, which is a great platform. Some references. Swift for Arduino, download where you can download it. Problem is, Apple does not allow compilers on the App Store, so we have to download it from this website. There is a demo on the App Store, but it's only to show the application. It doesn't do anything. My GitLab page, and well, I had great fun presenting this. I would like to thank Carl Pito, who created Swift for Arduino, and Daniel Steinberg for guiding me in this presentation. And I'll take your questions in the virtual site room after this talk. Thank you.